Welcome to the Precast podcast, episode number 50. So we are halfway to 100 with our episode initiative. Very excited for today's conversation. We're going to be talking and focusing primarily on cement, as well as obviously the concrete industry, the precast concrete industry. Kind of high level, we're talking about roadmap to carbon neutrality. And with us today is a gentleman named Josh. Josh, thank you very much for your time. I'm going to ask you before we get kicked off, could you please just give us a brief introduction of who you are and what you're doing and, kind of the topic at hand today?
Certainly. Thank you very much, Hugh. My name is Joshua Gilman, and I'm the manager of water resources and geotechnical support for the Portland Cement Association. So I've been with PCA since 2019. And before that, my background was in consulting in geotechnical and dam engineering, basically up and down the East Coast. And I currently live in New Hampshire with my family. That's really about me. A little bit about the Portland Cement Association. It's been in existence since 1916. And it's the premier policy, research, education, and market intelligence organization that serves America's cement manufacturers. So our members make up the majority of U.S. cement production capacity, and they have facilities in all 50 states. And really the goal of and the mission of PCA is to promote safety, sustainability, and innovation in all aspects of construction. And foster continuous improvement in cement and manufacturing distribution while promoting economic growth and sound infrastructure investment.
Very good. Okay. I just want to make sure I have this right. You said 1916. Is that correct?
Yes. Okay. That's right.
Very good. How many employees does PCA have?
PCA has a little under 50 employees currently, I believe. So that we're split up into different departments. So we have our market intelligence group. We have our research and technology and standards group, which I'm a part of. And then we have our government affairs group, as well as some administrative communications folks that serve our members' needs. So that's kind of all of us have our specialty and kind of work to the same goal, primarily to serve our member companies and their interests in cement manufacturing. Okay, so as we get into this episode, I just want to make listeners aware, we have a webpage that's specific to the Precast podcast. Every episode has its own entry on that webpage, and this episode will be one where you can download a PDF version of a presentation that we're going to be using as a guide as we talk through this episode. So if you are listening to this and you want to download that PDF document, please go to our website, shadeconcrete.com. You'll very quickly see a link to the Precast podcast, and you can do that if you're interested in that. Josh, with that being said, why don't we kind of get going here? Sounds great. So kind of talking about the broad topic of sustainability today, and that term's thrown around quite a bit, and there's a bit more to it than just the kind of the blanket statement of let's be more sustainable. So there's really what's called the triple bottom line of sustainability, and that incorporates the economic, environmental, and societal pillars of sustainability. That you really have to have all three of those to have a sustainable society. Related to the cement and concrete industry in our discussion today, we're going to look specifically at environmental sustainability and in particular climate change caused by greenhouse gas emissions, in particular CO2. So the levels of CO2 in the slide, the PDF of the slides, there's a graph that shows the levels of CO2 in the atmosphere over the last 800,000 years. And this is based on analysis of ancient ice cores and direct measurements in the atmosphere. And what it's showing is it's providing evidence that the CO2 in the atmosphere has increased dramatically, basically since the Industrial Revolution. And there's a lot of human activities that contribute to that, such as burning coal, oil, gas, and deforestation. And there is a component of CO2 emissions that's attributed to the manufacture of cement as well. But there is a misperception about exactly how much of that CO2 contribution can be blamed, I guess, on the cement industry. And in the PDF slides, there's another figure here that's showing, we call this the bubble diagram. And what it's showing is the embodied CO2 and embodied energy of different construction materials. And those materials in the upper right-hand corner have the higher embodied CO2 and embodied energy by mass. And embodied energy just means the amount of energy or CO2 that's emitted or consumed during the manufacture of that material. So it's emissions that are embodied to that material. So in this graph, if you look at the lower left-hand corner, you actually see concrete and cement are on the lower end of embodied CO2 and embodied energy by mass. So to the misperception that cement and concrete is just the worst possible material that can be used is just not, it's not the case. And there's more concrete used than any other material on the planet by a factor of about 10. So when we look at making improvements in the CO2 footprint of concrete and cement, the corollary there is that any improvements that we make, even if they're on the smaller end, have a significant impact when they get applied at the scale that concrete is consumed, both in the US and worldwide.
Josh, if I could just stop you. So again, we're on slide 6 of 45. As you go to the upper right side, that means it produces greater amounts of CO2, lower left side, less amounts. Is that correct?
Yeah, that's right. Higher embodied CO2 and embodied energy to the upper right-hand corner. And the next slide just shows the comparison of consumption of materials, different types of materials, and shows that concrete is, by a factor of 10, is consumed more than any other material on the planet. So to that end, that's why the cement and concrete industry has made a commitment to achieve carbon neutrality by the year 2050. And PCA on behalf of the industry has published a roadmap to carbon neutrality, and that was published in the fall of 2021. And what it does is it lays out the steps, starting at the cement plant and extending through the entire life cycle of the built environment that'll be required to lower the environmental impacts of the cement and concrete industry to carbon neutrality. And then looking at slide 9, this is the basis of the roadmap, and it's called the value chain. So the value chain is made up of the 5 C's, which are clinker, cement, concrete, construction, and carbonation. And this chain starts at the cement plant and it extends through the entire life cycle of the built environment. And each link of the chain provides specific contributions to environmental sustainability. But it will require the engagement of all cement and concrete value chain stakeholders. And that includes the owners, engineers, regulators, precast manufacturers, all of them.
Just one more question. Do you know the number? How many cement manufacturers are there specifically in the US? And then if we go to North America?
I don't know the comparison between the US and North America. There are a lot of cement manufacturing companies that are globally owned, so they're worldwide. So they may have locations in the US, Canada, Mexico, and worldwide as well. So on slide 10, taking a look at the value chain and the different components and where the responsibility kind of lies. So the clinker and cement links of the chain, that's what occurs at the cement plant. And cement manufacturers have been making improvements over the last several decades to reduce the amount of energy it takes to actually make a metric ton of clinker. And there's other steps and that are being implemented, such as increasing the use of decarbonated raw materials, increasing the use of alternative fuels to strive towards the goal of reducing the carbon footprint as much as possible. And we'll talk more about that as we look at each link in the chain. And then where the precast industry comes in is in the concrete and construction links of the chain, where they have control over the processes that consume energy or the consumption of materials, where choices can be made to use lower carbon materials and lower the environmental footprint of those materials that are being built for the use in construction. And then the final link of the chain is carbonation, and that's the natural process by which concrete that's exposed to the air absorbs and permanently sequesters CO2. So we'll take a look at all of these closer as we look at each link in the chain. And the first link of the chain we're going to look at is the clinker. And that's the key chemically reactive ingredient that makes concrete work. It's a hydraulic material, and we don't have concrete without clinker. So at the cement plant, raw materials, including lime, iron, silica, and alumina, are burned at extremely high temperatures, up to 2,800 degrees Fahrenheit in a cement kiln. And there's a chemical process that converts calcium carbonate, or the limestone, into a calcium oxide and CO2. And that CO2 that's created as part of this process accounts for about 60% of CO2 emissions from cement manufacturing. And then the other 40% is the burning of combustible fossil fuels to achieve those high temperatures in the kiln, as well as running the other mechanical components of the cement plant. That calcination that occurs that does generate CO2, that's the key chemical reaction to make that's required to make Portland cement and make it a hydraulic material and give concrete the properties that we use and need. So moving on to slide 13.
I guess one thing earlier in the conversation, Josh, you said that maybe there's different fuels that are being utilized, during the process of making the cement. I guess I'm assuming it's most likely would it be natural gas that's currently being utilized in terms of bringing temperatures up to 2,800 degrees Fahrenheit. Or are there any other fuels that cement manufacturers are using, or are there anything with solar or wind or anything that's being utilized as well?
Yeah, and I do have some talk about that in a few slides, but I mean, just an example, I visited a cement plant in Texas, and they were co-located on a site with a rubber tire, just like a automobile tire recycling facility. So they were able to sort the tires and find the tires that were going to contribute positively to the chemical makeup inside the kiln, which is where they're actually making the cement. So they were introducing those tires as an alternative fuel because they burn and create that additional energy that's required to heat up the kiln. But even the steel belts inside the tires were contributing iron that contributed positively to the ultimate chemical makeup of the clinker they were making. So that's just an example that kind of stuck out in my mind. Like the highways around Dallas where this plant was located are 10-lane highways, and there's an enormous supply of used tires, and it was really great to see that sort of beneficial reuse of tires in that way. So the cement industry in the U.S., the cement industry is, because of the CO2 footprint and the emissions that occur, it's one of the most heavily regulated industries in the country. So they're required to report emissions to the EPA, and the EPA's estimate, or based on that data, the amount of CO2 that's contributed or emissions in the U.S., the cement industry accounts for about 1.25% of CO2 equivalents in the U.S. itself. So there are other numbers that are thrown around about the cement consumption or the cement contribution to CO2 emissions globally. But this is the data that's aggregated by the EPA, showing that the actual contribution of the cement industry in the U.S. is 1.25%. And there's a lot of optimization that is going to lower that CO2 footprint, or the amount of CO2 that's emitted. And that includes increasing the use of decarbonated materials, as I mentioned, increasing the use of alternative fuels, and really pushing the efficiency and decreasing the energy intensity to make the clinker that's ultimately ground and made into cement. And there's transformative technologies that are also under development, such as using carbon capture, utilization, and storage, and reducing the clinker production emissions as well. Kind of going back to the use of alternative raw materials, the slide 15 kind of shows some of those materials that are being used. There's different lime-rich materials such as marginal limestone, paper sludge, sugar sludge, and these aren't just alternative fuels. So there's the alternative materials that are used in fuel for the cement plants, and then there's materials that are used to alter the chemistry of the clinker inside the kiln for the benefit of a better formulation of the cement and contributing to its performance. So there's lots of these different alternative materials that are being used, and the roadmap lays out targets of increasing the use of those materials by 2050. So currently they're more on the order of less than 5% of the overall formulation of the cement. So by 2050, the goal is to double that amount. Then on slide 16, we're showing the use of different types of alternative fuels. So looking even beyond the use of natural gas, we're looking at using gaseous waste from landfills, liquid wastes such as paint sludges, solvents, and all of these are typically wastes that come from other industrial processes. So these are materials that either end up in a landfill or are being stored, and really to find a way to beneficially reuse them while decreasing the flow of these materials to landfills finding a beneficial reuse of them. A cement plant is pretty ideal for that situation. So that also includes solid waste and pasty waste, such as plastic shavings, rubber shavings, as with the use of tires and other types of material. And as a result of the industry's efforts over the last 40 years, the amount of energy that it takes to produce a metric ton of clinker has been reduced by 40% since the 1970s. While that's fantastic, the industry does realize that more needs to be done, and the goal is to reduce the amount of energy by another 25% by the year 2050. And that there's a figure on slide 17 that shows that data. One of the transformative technologies that I mentioned earlier is the use of carbon capture, utilization, and storage. And this is something that there's a lot of money and effort being spent to understand how the most efficient process of doing this, and also to solve the problem of being able to implement it at scale. Because so basically it's taking the CO2 out of the emissions. So it would be taking the CO2 from the calcination in the kiln, taking it right out of the air and capturing it, storing it, and then finding a utilization for that CO2, whether it's going to be permanently stored underground or used in some other process in a beneficial way. There's challenges to doing this, and there's a lot of money and research being done through the Department of Energy and others. There's studies underway at 5 different plants in the U.S., in Texas, Missouri, and Colorado, to try to understand how how this technology can be implemented at cement plants, where that benefit may be the greatest along the cement and concrete value chain, but ultimately it could be implemented further down the value chain. But there are needs, and in addition to the information, the research gap, and the scalability gap that exists currently, there's other needs for pipeline capacity, because once that CO2 has been captured and stored, it needs to be transferred to the final location where it's either going to be permanently stored or utilized. So there'll be a significant need for pipeline capacity to move that material around. And there's also a significant need for energy, and a more robust power grid, because currently the CCUS process appears to use a lot of energy, and that amount of energy that's going to be consumed needs to be, wherever it's being generated, it needs to be transferred to the plant so that can be taken on. So now that we've taken a look at the clinker link of the chain, now we can take a look at the cement. And that's really, the cement is the binder in concrete that gives concrete its fresh and hardened properties that we use. So the clinker is ground finely, and then it's further optimized by blending it with other additions like gypsum and limestone to make Portland cement. And one of the ways to lower the environmental impacts of the ultimate cement product is to use only the amount of clinker that's required to achieve the performance of ultimately the concrete that we need, because that clinker does have the higher CO2 footprint as a result of the processes that we just talked about. So right sizing the amount of clinker is important. And in order to reduce the amount of clinker that's used in cement, we need to have a higher component of non-gypsum additions. And it's very important to choose the right cement specification for specific applications, because there's different performance requirements that there isn't just one gray powder. There's lots of different cements that can achieve early strength, sulfate resistance, low heat of hydration. All these sorts of things have to come into play when we choose and try to optimize our use of cement and ultimately of the clinker. So the goal is to take about a 90% clinker component in cement and reduce that to about 75% by 2050. But ultimately, that doesn't happen at the expense of the performance of concrete. That's an unacceptable thing to allow, and it's not in anyone's interest in the entire industry to allow that to happen. So figuring out how to maintain performance and the long-term durability that we expect from concrete while achieving these environmental impact reductions is the key.
Josh, I'm assuming there's a lot of work being done. I mean, as different options come up, I'm sure there's a lot of different creations of companies as well, but are you directly involved, kind of with the the different ASTM committees as different things are introduced, ensure that, quality of the ultimate concrete product is not having any challenges?
Yes, I'm involved in the industry, and the folks that I work with at PCA and products and standards, they're heavily involved in that, because ultimately that's one of the best ways to ensure that ultimately the concrete performance does not get sacrificed for as we move along this journey towards carbon neutrality, and as the industry changes as well. So there's lots of changes that are occurring in ASTM standards, such as for the fly ash standard that used to include natural pozzolans, that's being changed to a coal ash standard in order to incorporate the harvested ash that's becoming available in some markets, just by the changes in fly ash and coal-fired power plants that are coming offline in the U.S. So as the industry is changing, so are the standards to keep up with the trends and make sure that performance is maintained. And there's other organizations too, like ACI, in addition to ASTM, that are really at the forefront of recognizing where things are going and what changes are going to be needed to accommodate changes in industry and also maintain that performance in a general sense. As we talk about ASTM, there are 3 ASTM standards where cement is manufactured to in the U.S. So one of them, the first one, the oldest one, is the ASTM C150, which is the Portland cement standard. And that's where you'll find your type 1, 2, 3, 5 type cements. And that's been the cement standard for over a century, essentially, for cement in the U.S. We also have the ASTM C595 specification. So that's the blended cement specification, where your type 1L, 1S, 1T, 1P cements are. And those are 1L is a Portland limestone cement, 1T is a ternary blend, 1P is pozzolan, 1S is slag. And then the lesser used standard is the performance specification, ASTM C1157, where you'll find types GU, HE, MS, HS, and those are just general use, high early strength, moderate sulfate, etc. So the trend in the US is the increased use in blended cements, and in particular, the type 1L or Portland limestone blended cement. So as the shift towards improving the environmental impacts of concrete has occurred, the trend of consuming and the demand for a blended cement that can do that has increased significantly in the U.S. in very recently. So 1L is as I said, is a Portland limestone cement, and it was developed to be able to replace ASTM C150, like type 1, type 2 cements, at a 1-to-1 ratio. And testing would be required to confirm the fresh and hardened properties, but essentially was intended to be close to a 1-to-1 replacement, while providing same performance and workability with the same dosages of SCMs. And it provides up to a 10% reduction in carbon footprint of the PLC concrete versus the type 1-2 concrete. And there's a lot more information on PLC at www.greenercement.com. But we'll take a look at some more of the information about PLC in the next few slides. So PLC is not a new cement. It's actually been in the specification since 2012 as a type 1L. There's been quite an evolution in cement specifications, because actually Portland limestone cement has been used prior to being included in the C595 spec, and it was used as early as in the early 90s as a C1157 cement in the US, because it met the criteria and the specifications of that spec. The big benefit of PLC is really it can be demonstrated in the industry-wide environmental product declarations for cement. So this is slide number 25. So in 2016, the industry put out a industry-wide EPD for Portland cement, and recently updated that EPD in 2021 so that we can make a comparison of the global warming potential from 2016 to 2021. And what we see is there was an industry-wide 11.3 reduction in global warming potential of Portland cement between 2016 and 2021, which is a fantastic number. But it gets even better when you compare the EPD for Portland cement in 2021 to the first ever Portland limestone cement EPD, also developed in 2021. And what that shows is an additional 8.3% reduction in global warming potential when you're switching from Portland cement to Portland limestone cement. That's significant, and it's excellent to see that that sort of progress can be made so early in the process of this roadmap implementation towards carbon neutrality by 2050. And what's really exciting is on slide 26, as you see the portion of cement consumed in the U.S. that is a blended cement material, that's increased significantly over the last 18 months. So prior to 2019, blended cements didn't account for more than 3% of the total cement consumed in the U.S. And now we're approaching 27% of cement being blended cement, and most of that blended cement is PLC or type 1L cement.
That's a lot of growth since 21.
It is, and it's based on the demand of the industry for a dramatic improvement in environmental impacts of the concrete and the cements they use, and also switching of some of the cement manufacturers over to producing type 1L. And the exciting part is that those reductions, while 8.3% sounds great, when you start to apply that on a significant scale of all the cement that's consumed in the U.S., so on the order of 100 million metric tons a year, we're starting to talk about very significant improvements. And part of the growth in acceptance is of use of type 1L is there's the DOT acceptance of the material into their specifications. So from 2005, there was a lot of consideration of accepting 1L. Now looking ahead to 2022, almost every state in the U.S. is either already incorporated type 1L into their specification as acceptable or is planning to do so at the next publishing of their standards.
Josh, do you know what's the hesitation for Connecticut, New Hampshire, Maine, Rhode Island? Might you know those reasons?
Yep. Well, there's no longer hesitation. It's the next time that so the different state DOTs publish new specifications every 4 years, 6 years. It kind of varies on the rotation. So they aren't going to publish a new standard ahead of schedule, but at the next publishing, the C595 1L cements will be included as an option or as acceptable in concretes.
Okay. Do you know, might there be any limitations where they do not allow 1L to be utilized? Like bridge decks, or are you aware of any applications where 1L is not allowed for use based on actual applications of the infrastructure?
I'm not aware of any infrastructure applications where it's not allowed. And it's part of the reason is that the way it was developed was basically PLC has up to a 15% component of uncalcined limestone incorporated, and then there's optimization of the mixture, and it's often ground a little finer than the type 1 and 2 cements so that it performs similarly. And there's lots of lots of research and data to support the different properties of Portland cement concrete and PLC concrete performing similarly in heat of hydration, strength gain, ASR. So performance is typically similar or better for type 1L.
Great.
And there's special properties for PLCs, kind of similar to the special properties of the C150 spec, where you had your type 2 is moderate sulfate resistant, type 5 high sulfate resistance. So those special properties also exist for PLC, but they're handled a little differently. So on slide number 28, you can see that everything is a type 1L cement, but then there's a modifier. So like an L1L MS is a 1L moderate sulfate resistant, 1L MH, a moderate heat of hydration, et cetera. So those special properties that we're used to seeing, that folks are used to seeing in C150, also exist for PLC. So now taking a look at concrete, which is where the next link in the value chain, and there's been significant progress towards optimizing concrete mixtures in all sectors of infrastructure, including in precast industry as well. And really the keys to optimizing concrete are to use the right amount of cement, which means we're using the right amount of clinker so that we're not putting an embodied CO2 into our concrete mixtures that's not necessary to achieve the ultimate performance and durability of the material. So Increasing the use of supplementary cementitious materials is another way to optimize these mixed designs and take a little bit of the cement and the clinker out of it, while also achieving these SCMs are typically contributing to the performance of the concrete mixture in a positive way, such as fly ash with the ASR resistance, if that's what's needed, or improving the workability, reducing water demand, that sort of thing. Reducing concrete plant energy consumption and delivery energy consumption. So whether it's a ready mix plant or a precast concrete plant, just reducing the amount of energy it takes and improving the processes to doing can also attribute to lowering environmental impacts. Using performance engineered mixtures, and ultimately, eventually, utilizing carbon capture, utilization, and storage to reduce the release of CO2 emissions altogether. And one of the shifts in kind of the development of projects is to allow for a shift from prescriptive specifications to performance specifications. And what that does is it really incentivizes innovations and allows the contractor or precast manufacturer or concrete ready mix concrete producer to use the resources that are regionally available to them to ultimately provide the performance that's required on the project, while providing the opportunity to lower the environmental impacts of the mixture by using different types of SCMs and admixtures in that way. And just allowing it prevents inherent over design that can occur in the case of prescriptive specifications, because not every structure needs the same amount of durability or freeze thaw resistance. So a concrete that's interior to a high-rise building doesn't need the salt scale resistance that a sidewalk that's located outside in downtown Chicago would require. So just really taking a look at what are the needs of this structure that's being designed, and how can we specify the performance requirements of it and allows the contractor, producer, what have you, to tell us what the best way to achieve that performance is.
Josh, is it also fair to say that in optimizing concrete mixtures, the admixture companies are very much involved?
Yes, absolutely. So my involvement in ASTM and the PCA, and also our member companies, the cement industry as a whole, coordination with the admixtures, the supplementary SCM producers, manufacturers, all of these different components are going to be critical to the ultimate goal of achieving carbon neutrality, because not one solution exists currently that's just going to automatically make the goal attainable. It's going to be a combination of things, and also policy changes and research efforts dedicated to growing the technologies that are needed to actually achieve carbon neutrality. One of the things that our producers have been working on over the last decade or so is automating supply chain systems and just basically maximizing that efficiency throughout all components of their supply chain in order to optimize the materials that are being implemented into their processes and really achieve waste reduction and improved environmental performance. So taking a look at the construction link of the chain, and this is where the service life and use phase impacts are shown. And on slide 34, there's a statement that basically says, start with the end in mind. And what that means is basically, in order to really take a look at the impacts of a structure or a decision, and it can scale from the very largest infrastructure projects all the way down to much smaller implementations. But to really take a look at the impacts, we have to look at a structure throughout its whole life cycle. So that's not just the embodied energy and CO2 and the materials that are being used. It's what's happening during construction, what's happening during the use phase, and what's happening at the end of the useful life of a structure. Like, what are we going to do with that thing when we're all done with a bridge? Like, what's going to happen to it when it's reached its end of its useful life? And when we do that, it's not an either or proposition that we're looking at. It's an all of the above. So when we look at the full life cycle, we can design for strength and durability, and look at the embodied carbon and resilience, and consider everything holistically find the best approach and the best solution for a given infrastructure problem or what have you. So on slide number 35, this is the entire life cycle of a given piece of infrastructure, and it kind of demonstrates what I'm talking about here. So when you may have heard the term cradle to gate. So that's basically the embodied impacts that are inherent to the material itself. So everything when it comes to cement, everything that's happening inside the gate at a cement plant, all of the impacts there are embodied in the A1 through A3 product stage. There's other stages in the life that attribute to the environmental impacts of a structure, any sort of structure. So just a bridge, for example. So the construction stage, there's the transportation and the construction and installation processes that have emissions and CO2 that's being emitted as part of it. But then when you consider the entire life cycle of a bridge, say it's 100 years, the most of the time is going to be encompassed in the use stage of that bridge. So when cars are driving on it, any sort of use, the maintenance, the repair, replacement or refurbishment, if that has to occur. So there's opportunities during the use phase to really nail down and that's where cement and concrete typically starts to shine, because you have a lower maintenance product that lasts for a long time with a lower maintenance. And it's very important to really address the issue of environmental impacts, to look at the entire life cycle. So, and at the end of the life cycle, if it's a concrete bridge, that concrete has recycling potential and could end up being recycled. And in the ideal situation, we end up with a circular economy where that recycled material goes into a concrete mixture for another bridge, and then we're reusing that material and restarting the life cycle again in another phase. So when we talk about optimizing construction, optimizing and avoiding over-design, leveraging construction technologies, which is where performance-based specifications really drive and incentivize that, and ultimately incentivizes efficient buildings, designing for the entire service life, which ultimately decreases the repair and maintenance in the use phase of the structure, and makes it and lowering the overall impacts. And there are ways to minimize CO2 during construction. We're on slide 37 now. Sourcing local materials to reduce transportation emissions, maximizing the efficient planning of machinery, sourcing carbon neutral biofuels and renewable energy, and installing renewable energy on site, both during the construction phase and the operational stage. And as I mentioned, recycle and reuse of materials is ideal. Final link of the chain is carbonation. This is the natural process where all exposed concrete surfaces absorb CO2. So if you have a buried concrete element, that's not exposed to CO2 or exposed to the atmosphere, it's not going to absorb CO2. But what's occurring for that concrete that is exposed is the calcium hydroxide in the concrete reacts with carbon dioxide in the atmosphere, and it creates a calcium carbonate in water. And when that occurs, that is a permanent sequestration of the CO2. So it isn't, if the structure is demolished and recycled, that CO2 isn't emitted again. That's actually permanently sequestered. And the early estimates indicate that about 10% of the CO2 generated through the manufacture of cement and concrete is reabsorbed by the concrete in a building over its lifespan. Recently, the Intergovernmental Panel on Climate Change, or the IPCC, has recognized that the mechanism of carbonation and its potential impact on assessing climate change. So as an example there, if you consider a concrete pavement where you have very large surfaces that are exposed to the air, and those concrete pavements are just carbonating over the lifespan of them being exposed and in use. So there's a huge potential for that carbonation to have a significant, it's an unknown or unquantified impact of reduction of CO2.
Back to slide 39, Josh, at Shea Concrete Products, a large number of the products that we manufacture are, underground products that get buried. With that being said, they do sit in inventory. I guess I'm just kind of trying to, just think of different ways that we can, as a company, talk about things that we're doing or that the products can do, to be more environmentally friendly. We just received a LEED certification for our headquarters building. We do use renewable energy. We have 2 solar arrays at our headquarters, but I guess with the majority of our products being buried, I guess I'm kind of thinking here, as those products sit in inventory, is there anything that I could maybe look into to see how they may be able to absorb CO2 at that time? I guess that's something I'll look into.
Yeah, ultimately, when they are sitting in inventory, they are absorbing CO2. This is a very slow process. So if they were sitting there for 50 years, that would be really significant. But that would probably be not so good for the inventory management of Shea. But
that's correct. Yeah.
But there is work that's being done to try to drive research and really quantify how to understand exactly how much CO2 is being absorbed and what the potential for absorption of CO2 is. So, for example, if there's a structure that's been demolished, how can that structure be demolished and the material stockpiled in a way to maximize the amount of CO2 that's being absorbed as that material is sitting there waiting for a beneficial reuse? So these are kind of the questions that are being posed, and the smartest folks in the country that are driving this kind of research are the ones trying to understand it and solve it, and so that we can have some actionable items to implement in our various operations. So we're kind of at the end of the presentation slides here. I've just got a couple more, just looking at 10 major policy necessities. So it's very important that there's a lot of decisions that can be made by the stakeholders in the value chain, from the cement plant through the engineers, owners, producers. But there are regulatory changes that are going to be required as well to try to innovate, to promote the innovation that's going to be required to ultimately achieve the ultimate goal and maintain a level playing field. So research and development and innovation, certainly going to be financial incentives and support. The shift to performance-based material standards, that's a tough hill to climb, and there's a lot of challenges there. But starting it through from the federal government all the way down through municipal and owner level specifications, there's an education that has to be implemented there to try to make that shift and for the ultimate goal down the road, and achieving market acceptance, community acceptance as these materials, these newer materials that achieve lower global warming potential are rolled out. The onboarding of those and acceptance of those will be important. Really striving to implement a full life cycle analysis when it comes to decisions for infrastructure is really going to be a key, and really hopefully drive us towards the cradle to cradle life cycle based procurement. So there's near-term goals, the things that can be done now, such as replacing raw materials with recycled materials and using low carbon materials such as Portland limestone cement, and optimizing designs to minimize waste and over design. And then midterm goals are the increased use of alternative fuels and renewable energy. And ultimately, long term, we're looking at carbon capture, utilization, and storage, or the CCUS, and other newer cement blends, such as other blended cements like a ternary blend, where there's actually 3 components to the blend, further reducing the clinker while using those other SCMs to optimize the performance of the concrete. And since the roadmap has been implemented, there's been a lot of success and a lot of progress so far. So maybe the biggest example, the most illustrative example, is the increased use of Type 1L cement under concrete, low embodied carbon concrete specifications through the GSA, and there's actually more than 80,000 environmental product declarations for ready mix concrete available in the U.S. So there's been extensive growth in basically having this tool to compare the global warming potential of concretes that are being made, and this is driven by the owners and the projects that are making this a requirement to show us what's your global warming potential and do better. And ultimately, it's an exciting time to be in the industry, cement and concrete industry, and with these types of dramatic changes occurring. And it's exciting to see how much progress has been achieved already. And I'm excited. I'm kind of in the middle of my career, maybe the early middle of my career. So I'm excited to see what the next 10, 15, 20 years looks like, and how far along we get, because ultimately 2050 is the ultimate goal for carbon neutrality, but it's very attainable to achieve that much sooner. And there's a lot of momentum and a lot of exciting things that are occurring that demonstrate that may happen.
That's great. Josh, I apologize if I missed it, but when did this initiative start?
PCA published the roadmap in fall of 2021. So it's been, I mean, but it's not fair to say that that's when everything started. This has been, I mean, you could go back to the 1970s when cement manufacturers were making improvements to the amount of energy their plant operations were using. And there was a 40% reduction over the last 40 years. So it's been understood that improvements have been needed to occur, but this represents a dramatic commitment. It's a significant commitment, and it also is PCA and the cement industry is leading this commitment on behalf of the cement and concrete industry to achieve revolutionize the use of cement and concrete in the U.S.
Josh, does PCA have its own annual conference, or does PCA work with like the NPCA or other trade organizations that have annual conferences or conferences throughout the year?
Yeah, so the IEEE, PCA partners with IEEE, and they put on a cement industry conference. So it's the premier cement industry conference in the US and one of the premier events in the world. And that usually occurs in springtime. So somewhere in March or so. That's kind of the big cement one. So, and in my role, we're also the NRMCA, National Ready Mix Concrete Association. We work very closely with them, and also the American Concrete Pavement Association, in addition to the other organizations that we're part of. So ACI, ASTM, the list is too long. So NRMCA has conferences, and there's a lot of they've just launched an award for concrete innovations, and particular for improved sustainability. And I mean, there's lots of support from our partner organizations in ultimately where we're going.
Well, Josh, this has been very educational. I really appreciate your time. And again, when we have this up live, folks that participate will be able to download the presentation that we've been utilizing as a PDF file, so they can utilize it as they listen along as well. Just want to point out on slide 45 of 45, you have access to Josh's contact information in terms of his email address if you want to reach out directly with any questions or comments. Josh, we put on in-person technical engineering seminars at our headquarters facility in Amesbury, Massachusetts, and I am going to try to see if you might be local, and if we can get you to attend and present at one of those in the future. So I will start that process after we wrap up this podcast. How's that?
That sounds great. I'm happy to say I am local to New England once again, and I'd be happy to participate.
Yeah, very good. Okay. Well, Josh, thank you again. I want to thank our listeners and supporters of the Precast podcast. We'll have this episode up shortly, and we'll look forward to getting feedback. So thank you again. Thank you very much.